H2CO3. This is the H2CO3 Lewis structure, carbonic acid. Hydrogen has 1 valence electron. We have 2 hydrogens, plus 4 for carbon, plus 6 for oxygen, times 3, for a total of 24 valence electrons. Whenever you see hydrogens in front of a polyatomic ion like CO3, NO3, or SO4, it's going to be an acid, and you're going to need to put those hydrogens attached to the outside oxygens. So we'll put the carbon at the center, and we have 3 oxygens. We'll put 3 oxygens around it, and then we'll put those 2 H's on the outside of the oxygens. So we have a total of 24 valence electrons. We'll put 2 electrons between atoms to form chemical bonds. So we've used 2, 4, 6, 8, 10. Then we'll form octets for each atom. 12, 14, 16, 18, 20, 22, and 24. At this point, the hydrogens have 2 valence electrons each, so their outer shells are full, and the oxygens have 8 valence electrons each, so they have octets. Their outer shells are full as well. However, the carbon only has 6 valence electrons, so it needs 2 more to form an octet. What we can do is take 2 valence electrons from this oxygen and move them to the center and share them in a double bond. By sharing the valence electrons in that double bond, oxygen has 8 still, but now the carbon has 8, and we're still only using 24 valence electrons. So we've used all 24 valence electrons, and each of the atoms in H2CO3 has a full outer shell. So that's the Lewis structure for H2CO3. We could check our formal charges. If we did, we'd find that the formal charge for each atom in H2CO3 is 0, making this the Lewis structure for H2CO3. This is Dr. B, and thanks for watching. The CO3 2- Lewis structure of the carbonate ion. Carbon has 4 valence electrons. Oxygen has 6. We have 3 oxygens. And this -2 means we have an extra 2 valence electrons. Add that all up, 4 plus 18 plus 2, 24 valence electrons. Carbon is the least electronegative. Put that at the center. 3 oxygens go around the carbon. We'll put 2 electrons between the atoms, form chemical bonds. We've used 6, and then around the oxygens, 8, 10, and 24. So we've used all 24 valence electrons. All have octets, 8 valence electrons. The carbon, however, only has 6 valence electrons. Let's move 2 valence electrons from here to form a double bond with the carbon. So this oxygen still has 8 valence electrons, but now the carbon has 8 valence electrons, and we're still using only 24 valence electrons. So the formal charges do make sense here because the black oxygens here and here both have a formal charge of -1, and the carbon and the other oxygen are 0. So -1 plus -1, that does match up with what we have for the carbonate ion here. Because of that, this is the best Lewis structure for CO3 2-. There's one last thing we need to do. Because the CO3 2- ion has a charge of -2, we need to put brackets around our Lewis structure and put that -2 outside so everyone knows that it is an ion and it has a -2 charge. And that's it. That's the Lewis structure for CO3 2-. This is Dr. B, and thanks. H6 Lewis structure. There are 3 ways we can draw it. The most common is benzene. I'll explain how to do that, and then I'll show you the other 2 ways that we can draw the C6H6 Lewis structure. So we have a total of 30 valence electrons to work with. For benzene, we're going to put the carbons in a ring structure. Then we'll put the hydrogens outside of the carbons. So we have our skeleton structure. So let's put 2 electrons between each of the atoms to form chemical bonds. So we'll put them like this, and we'll go around and do that for all of the atoms. So we have 6 valence electrons, so we'll put, 2 here, 2 here, and then 2 here. But you can see right away we have octets on these carbon atoms, but these other 3 only have 3 bonds. So they only have 6 valence electrons, and they don't have a full outer shell. So we're going to need to form some double bonds. It looks like we'll need 3 double bonds. So let's take these 2 valence electrons and form a double bond between these 2 carbons. So now these 2 carbons here, they have 8 valence electrons in their outer shell. We can form another double bond, but we can't put it right next to the one we just formed, because then that carbon right here would have more than 8 valence electrons. So we'll need to alternate our double bonds. Let's take these 2 here and form a double bond here. And finally, let's take these 2 and form a double bond right here. So now we're still using 30 valence electrons, but each of the carbons has 8 valence electrons, so its octet is satisfied. So this is a viable Lewis structure for C6H6. In fact, it's called benzene, and it's quite common in organic chemistry. In fact, since benzene is commonly used in organic chemistry, there's a number of other ways we can draw it. These structures are intended to make it easier to draw the benzene Lewis structure. You could also draw the C6H6 Lewis structure like this, or like this. There are probably even some other ways that I haven't thought of. So that's the Lewis structure for C6H6. Probably the most common will be the benzene. That's probably what you would be expected to know. But there are other isomers or ways to draw the C6H6 Lewis structure. This is Dr. B, and thanks for watching. This is the Cl2CO Lewis structure, carbonyl dichloride. For Cl2CO, we have 7 valence electrons for chlorine. We have 2 chlorines plus 4 for carbon and 6 for oxygen for a total of 24 valence electrons. Carbon is the least electronegative. We'll put that in the center. Let's put the chlorines on either side, and then we can put the oxygen on top here. We have 24 valence electrons for the Cl2CO Lewis structure. We'll put 2 electrons between each of the atoms to form a chemical bond. We've used 6. Then we'll go around the outside, 8, 10, and 24. So we've used all 24 valence electrons, but the central carbon only has 6 valence electrons. The other atoms do have octets with 8, so we need to fix that. We can take 2 valence electrons from the oxygen here and share them between the oxygen and the chlorine to form a double bond. We're still only using 24 valence electrons, but the oxygen, it still has an octet, and the carbon now has 8 valence electrons because of that double bond we formed with the oxygen. So we've used all 24 valence electrons. We've satisfied the octets on each of the atoms. So this is the Lewis structure for Cl2CO, and this is Dr. B. Hi, this is Dr. B. Let's do the Lewis structure for CS2. On the periodic table, carbon's in group 4, sometimes called 14, so it has 4 valence electrons. Sulfur in group 6, or 16, it has 6. We have 2 sulfurs, so let's multiply that times 2. 4 plus 12, 16 valence electrons. Let's draw it. Carbon, the least electronegative, goes in the center, and then we'll put the sulfurs on either side here. Now we want to add our valence electrons. Remember, we've got 16 to work with, so we'll put 2 between the atoms, and then we'll put them on the outside. So we have 2, 4, 6, 8, 10, 12, 14, 16. We've used those 16 up. Let's see if we have octets. 8 on that sulfur, 8 on that sulfur. Those have full outer shells. But in the middle, carbon only has 4. So we've got to fix that. We can take and move valence electrons between atoms and share them, so that the sulfur has 8 now still, but the carbon has 6. We're almost there. Let's share this side here to be symmetrical. And now, again, we have 8 on that sulfur, but the carbon now has an octet. So it's stable and its octet is satisfied, and we've used only the valence electrons that we had available. So we have this structure here, and we can also write it as what is called a structural formula, and that's going to look like this right here. And with the structural formula, a line represents a pair of electrons. So we have 2 pair of electrons here, and we have these 2 lines here. That's the Lewis structure for CS2. This is Dr. B, and thank you for watching. Hi, this is Dr. B. Let's do the Lewis structure for H3O+, the hydronium ion. On the periodic table, hydrogen's in group 1, 1 valence electron, but we have 3 hydrogens, plus oxygen, group 6, or 16, 6 valence electrons, and this plus sign means we've lost a valence electron, we've lost a negative charge, so we actually need to subtract 1, and that gives us 3 plus 6 is 9 minus 1, 8 valence electron. Let's put the oxygen at the center. Hydrogens always go on the outside, right, like that. And let's put some valence electrons around the atoms. We'll start by forming chemical bonds. 2, 4, 6. We have 2 more. Let's put them up here on the oxygen. 8. So hydrogen only needs 2 to have a full outer shell. So the hydrogens are all good. Oxygen needs 8. It has 8. And we've used up all of the valence electrons. We'll finish by putting brackets around it, like this here, to show that it's an ion, and put a plus charge up here, so everyone knows that it's a positive ion, a cation. That's the Lewis structure for H3. Hi, this is Dr. B. We're going to do the Lewis structure for NF3 nitrogen trifluoride. On the periodic table, nitrogen is in group 5, or 15, so it has 5 valence electrons, and then fluorine is in group 7, or 17. It has 7. We've got 3 fluorines though, so multiply that by 3, and that equals 21 plus 5 is 26 valence electrons. So nitrogen is the least electronegative, so that's going to go in the center here, and then we'll put the F's, those fluorines around there, and we have 3 of them. Okay, so at this point we've got 26 valence electrons to work with, and let's first put them between atoms to form that chemical bond there. So 2, 4, 6, and spread them around the outside now. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and we'll put the last 2 here, 26, which is what we had to work with, and to give nitrogen an octet. Let's check and see if everything has 8 valence electrons or an octet. Fluorine has 8, this fluorine has 8, and then this fluorine right down here as well has 8. Their outer shells are full. And then nitrogen, well, it has 8 too. So that's the correct valence electron count for each of these. So our Lewis structure is done. And we could also draw it as a structural formula. And that would look like this right here. That is the Lewis structure for NF3. This is Dr. B. Thanks for watching.
Next molecule we have an ion. It's called aluminum tetrachloride. And why would aluminum tetrachloride be an ion in the first place? Well, aluminum only has 3 valence electrons. So if it's going to form bonds with 4 chlorines, chlorines have 7 valence electrons, so they're looking for single bonds to come up with that 8 valence electron. You probably need an additional electron to accomplish that. Let's find out by drawing the Lewis structure and see what we get. Aluminum is going to go in the middle. It's the lowest electron.